Okay, hello everyone. So, in the last section, we discussed about how the solution should look like for a higher order differential equation and what should be our general approach towards solving a higher order linear homogeneous differential equation. Then we discuss about the non-homogeneity too. So, what was the main thing? If you have a homogeneous linear differential equation, you find these pieces of the solutions, which we call fundamental set of solutions. These solutions are not only solutions for the differential equation, but they are linearly independent from each other. They are not constant copies of the functions of each other. Okay, so that was the idea. And we are going to develop methods to solve homogeneous linear differential equation based on just that fact. Okay, all right. So for now, let's just focus on second order linear homogeneous differential equations. Okay, all right. So we have a second order homogeneous linear differential equation. So since this is second order, how many solution pieces you need, or how many solutions should be there on the fundamental set? 2, right? Okay, so we need y1 and y2. Good. Now what is the key thing about y1 and y2? So this is a set of functions. y1 and y2 are linearly independent. Now the most simplest way to explain this is y2 is not a constant multiple of y1. That means y2 is not c times y1, or y1 is not c times y2. Okay, so they are two independent functions. Good. Now we can write that statement in a different way. Think about this. I'm going to take y2 and I am gonna divide y2 by y1. Now you tell me, what should we not expect? Yes. If you divide y2 by y1, what we should not get? We should not get a constant, right? And that is the whole point about being linearly independent. Okay, and this method that we are going to learn today is basically based on just that fact. So y2 divided by y1 is not a constant because they are linearly independent. They are not constant multiples of each other. So what should be y2 over y1? It should be a function. Let's call it u. It should be a function, right? That is how you become y2 and y1 linearly independent. All right. Let's rewrite this in a nicer way. y2, let's rewrite this as u times y1. Okay. Alright. So second solution is first solution times a function, unknown function. Okay. Right. Now the method that we are going to learn in this section is called reduction of order method. And the reduction of order method starts with this specific step. You have a second order homogeneous differential equation, linear one, but also think, if you know, what if you know a one solution? That means, what if you know y1? Then can you find y2? Because we know y2 is some unknown function times y1, right? So if we can find u, then I get y2, right? So that is the whole goal of reduction of method. One goal, okay? One piece. So you know y1, you find this u. That is your target. Find this u, the unknown function. Then multiply y1 by u. Then you get the second solution. Then we can write the final general solution as y is equal to c1 y1 plus c2 y2, right? A linear combination of two linearly independent solution will give you the final general solution for the differential equation. Okay, now you understand the whole goal? Good. There's another point I will discuss in the next video. Okay, so another thing we need to get clear is, to use this method, we need the standard form of a second order linear differential equation. Now we learned the standard form. Remember where? We talked about that, right? You should remember. We talked about the standard form of a first order linear differential equation. And if we have a first order linear differential equation that looks like y prime plus p times y is equal to q, where p and q are only functions of x. This is standard form. Important thing here, coefficient of y prime is 1. That is the standard form of a first order linear differential equation. But now we are dealing with second order linear differential equation. Well, what is the standard form for a second order linear differential equation? Let me write down y double prime plus p times y prime plus q times y. Now let's say it's homogeneous, okay? Alright, this is the standard form. Clear things. Look at the difference. Look at where p is and write down in your notes. This is very crucial and don't get these two mixed up. P in the linear differential equations, first order linear differential equations, p is the coefficient of y. But in second order differential equations, p is the coefficient of y prime. So notice that, don't get mixed up. And in a second order differential equation, being standard form means you need the coefficient of who to be 1? Y double prime to be 1. That means the leading coefficient should be 1. So this is what it means to be standard form in the second order linear differential equations. Good. So let's do an example and wrap it up, right? Okay, so x square y double prime minus 3xy prime plus 4y is equal to 0. Excuse me. So what should we have? Coefficient of y double prime to be 1. Here we have x square. So let's divide the whole equation by x square so that we get 1 as the coefficient of y double prime. But when you divide him by x square, we should make an important assumption, right? To be mathematically precise, x square shouldn't be 0, right? And we learned that a leading coefficient shouldn't be 0 anyway, because we cannot divide by 0. So x square cancel out here, so we get y double prime plus 3x over x square. Well, 1x cancel out, not plus, minus 3y over x plus 4y over x square is equal to 0. This is the standard form of this differential equation. And what is p? P is the coefficient of y prime for second order differential equations, which is negative 3 over x. Q is the 4 over x square. Now one thing very important, you have to identify p correctly in these type of problems also. Otherwise, just like that integrating factor method, you're gonna get totally screwed if you didn't identify p correctly. So that is something you should have in your notes, and that is something you should have in your mind when you're going to exams and when you go to the homework too. Okay? Alright, thank you. See you in the next video.